This is Twitch, right?
This is Twitch, yeah.
Welcome to Advanced Fortnite Opponent Humiliation Techniques. We're really talking about color. We're going to start here, primary colors. Is this something they can see? Board?
Yeah, it is.
Going from primary colors, and we're going to end right here. Ooh, hey.
You can point over there again. I'm sorry, I didn't have that.
Oh, I'm sorry. We're going to start here with primary colors. And when we're done, we're going to end here with that plus and minus and the 6 Fs. And Brandon has asked that we keep it an hour, so I got a countdown clock going. This will be a record. We can do this. We can do this together. So let's start. We're going to start here on this side with primary colors. And I'm asking you here in the classroom, and then also those on Twitch, and then you also have a back channel that some people are on, correct?
Yeah.
Primary colors, let's identify them. What are the primary colors? So they start rolling in and you just relay them, is that?
Yeah, there's a big delay though. So
Yeah,
you might
that's
wanna
okay.
answer the question
That's okay.
yourself here or ask our in-person.
Do you know primary colors?
RGB,
What are the primary colors?
red, green, blue.
Okay, we got red, green, blue. Any others? Anybody else like to weigh in?
You know, I have a first grader. He was telling me that the primary colors are not red, green, blue.
Oh, what's first grader telling you?
Blue, yellow, I think red.
Okay. So let's test this one, because this list right here on the left does not have yellow. But if we mix blue and yellow, what do we get?
Green.
We get green. Now here we got green already. So what's the difference between these two things? I mean, we all know from what grade? First grade?
First grade.
We all know from first grade that if you mix blue and yellow, you get green. And so maybe we should talk about what primary colors are. There's 3 primary colors, and all of the other colors can be obtained by mixing a combination of the primary colors. So we've got this difference between these two lists. This is the one that you're familiar with. You know that to get purple, you'd mix red and blue. And to get orange, you'd mix red and yellow. You've been doing this your whole life. So you recognize that that's a truth. But then we've got these things. What happens when you mix red and blue over here? Or red and green? And what's the difference between these sets of primary colors? Let's start. Let's start. Just make sure we're on the same page. Can we all agree? Blue and yellow paint mixed together is green. Got a thumbs up? Yep. Okay. So when you think about paint, you think about mixing those colors. There's an element there that's very important, and that is the light in the room. So everybody, for the purposes of this discussion, let's all agree that this is red. We're going to call this red. We're going to define it red. So my question to you, I got my box. It's an old box. So you saw the red folder. What color is the red folder right now? Anybody?
Still red.
We got still red.
I think it's black.
Think it's black? Anything else? I wish probably, I see what happens here. Let's test this. If I do this, is this gonna mess things up? Maybe there's a way that you could digitally do this. Red folder. Oh man, there we go. Red folder. Is it still a red folder? You guys are probably seeing the same thing we're seeing here. And back to the lights being on.
Do you want to try the box trick?
Let's do the box trick. So I've got red pen. Put the red pen in the box. And I'm gonna put a camera. What?
Keep speaking towards that mic. If you
Oh, yeah, sure. Is this the camera's
Yeah,
going
this
in
is the
box?
camera. In fact, you know what? I'm gonna flip the camera around here. Hey, everybody. I'm gonna hand the camera to Anthony.
All right, well, we'll see what happens. Okay, so it's facing me. Let's put it in the box where we can see the pen. There. Okay, see the pen?
Yeah, they got the live stream in the box.
And then I'm gonna close the box. Okay. Can you see the pen still? Can you see the red pen? Is it red?
Doesn't look red on the screen.
Okay. So the question to the group, and we really have to be on the same page at this, is the pen red when it's in the box? Is the pen red when it's in the box? That's the question. So I need some yeses and nos.
Yes and no?
Ooh, we've got going a little bit beyond. It's hurting my brain. Anybody have a definitive yes or no in the stream?
You got my stream up there, so I don't know what the chat room is saying.
Oh, I have it. I'm gonna hand it back.
Yeah, hand it back. Someone in the chat room is saying colors are based on light reflection. No light means no color.
Wow. Okay. I like that. And that holds true over here on this side. Blue, yellow, red. If these are our primary colors. Let's talk a little bit about that and how that works in terms of light and color. So here's me in the desert, sitting on a camel with a chihuahua's head. It's very hot, doing a lot of traveling. So I have to choose my attire. I'm gonna choose, because it's stylish, all black. Is that a good idea?
Probably not.
Probably not a good idea. Why might that not be a good idea?
No answers in the chat room yet. We're waiting.
Oh, okay. There's a delay, it's fine.
When you watch from home, can you usually tell the delay as I wait for answers to come in? Can you usually feel the delay when you're at home? Oh, what? Someone replied, nope, black absorbs thermal energy.
Ooh, it does absorb thermal energy and also the light. So what might be an appropriate color for me to wear in the desert if I'm trying to stay cool?
What about white?
Yeah, okay. So I'm gonna wear white because white is going to reflect the entire spectrum of light away from me, and thus keeping me cooler. So if we can agree that far, I think we're moving along. But then we gotta figure out how to get to this right here. So if, using the primary colors that we're all used to, blue, yellow, and red, then when we have this red envelope, the light from the lights in this room is bouncing off of this envelope, and it's absorbing the everything but red, and red is bouncing back to you, and you are able to perceive it. So if I'm trying to get red into your eyes, then I can absorb the spectrum and bounce back one particular color, and that's what you're going to see. An alternative to get red into your eyes might be what? What source could I use to get you to perceive red? If I don't have paint, I don't have this envelope, what can I use? I'm going to use my watch. If that's cool. It's not what, there we go. Okay, so red going directly into your eyes. Now let's test something with my watch. I'm going to do the same thing. We won't use the box. We're going to turn the lights out. Can you still perceive the red? And of course, if we put the camera in the box with this light, we would see the red in the box. Can we try that?
Yeah, we can try it.
All right. So just go ahead and just kind of set it in there. So we see the red, box is covered, relatively speaking. So the light in the room has no influence on that. And that is the difference between subtractive colors and additive colors. This set, blue, yellow, and red, these are subtractive, and they are going to absorb all the other colors and reflect back to you the color that you see. So when you mix them, it's going to be a different result than if you were to mix these, which are additive colors. And this is direct light. It's going from a light source to your eyes. There's no reflection of light off of a color. It's direct light going into your eyes. And these are the primary colors for that: red, green, and blue. And we're going to, in a little bit, kind of see what that combination is. In fact, let's do that.
Fix right now, unfortunately.
Okay. Is the tunnel gone?
No, it's back.
Okay, hold on just a second. Is the tunnel gone now?
I'm trying to give it a no. I'm trying to give it a sec because there's such a delay. There, maybe that did it, or at least whatever window's up right now did it.
There you go. Alright, you are live in photo.
Okay, sweet. And is audio coming through?
I'll tell you in just a second. Go ahead, start talking.
Testing audio. Okay, sweet. Okay, so I just went in Photoshop, I just went to the color picker that comes up if you click one of these colors. And we're looking at this mixture, red, green, and blue. And so if I pick something like that we've identified as a primary color, let's look at red. Go. And And then we look over here at this R, G, and B. We have a value, a higher value for red, and then no value for green and blue, and we get red. If we look at some of the other colors that were in the primary colors for subtractive colors, one of them was yellow. So if we get to yellow, we see that to actually make yellow using additive colors, then we need to maximize red and we need to maximize green. And basically red and green mixed together make yellow. That's not what you learned. Because when you were growing up, the focus was on the primary colors, and they actually were not what you learned. You learned blue, yellow, and red, but
Can you hear us now on the live stream? I try again right now.
you mean,
Gotta agree.
okay, sweet. Okay, so CYMK, cyan, yellow, magenta, and the K stands for black. And the K is at the end of the word black, but if they were to have used B, people would have assumed blue, so K makes a lot more sense. And the reason that we've got 4 over here, and the other one is RGB, red, green, blue, is because of this, this K. Because when you're talking about theoretical colors and mixing colors, then the idea is that when you take all of the primary colors, at least when it comes to subtractive colors, the paints that you used to, theoretically, if you were to mix them equally and proportionally, then you would have black if they were in the same amount. But in reality, we use chemicals found in nature and man-made chemicals to make dyes that don't actually follow the theoretical mix. So if you were to mix most inks that are used in printers or toners that are used in printers, and you were to mix them equally, you'd end up with some kind of dark puke brown, basically, which is not black. So what we do in printers, we add an extra cartridge that's already mixed as black so that we can get a true black. So that's why we have this. When you're mixing light and you mix all the primary colors together using additive colors equally, you will get white. That will be the result. And that happens in reality as well as theoretical. And any absence of all 3 of these colors will result in black if we're talking about additive colors. With ink, there's no way to produce white because you are basically not using any paint, and so you need to have a white piece of paper to experience that. And this is dependent upon the light in the room. The light in the room will affect those things. Here, not so much. And making this switch from blue, yellow, red as your primary colors to RGB is going to take some practice. But you'll need to be thinking about colors in those terms because the light that you're working with is coming from your screens. And it makes it very difficult to cross mediums from additive to subtractive. So when people design things on the computer and they want to print them out, it becomes a little problematic because you've got to compensate. Can I go back to Photoshop?
Yeah, totally.
Test.
Yeah, let's try that.
Okay. So I'm not sure when we cut out, so I'm going to repeat this. Photoshop is aware that when you are working with additive colors on your screen, that it's going to be very difficult to translate those to subtractive colors. But it does give you some help with that. When you choose a color, then next to that color, there's this warning symbol. It's a triangle with an exclamation point, and it's basically warning you that what you see on your screen is not what you're going to see when you print, that this color is going to be more accurate. You see how that moved from the corner over here a little bit. This is something that can be printed, and most of that has centers around brightness. Whatever. Your screen can be as bright as you need it to be, but a piece of paper, whatever the ink that's on a piece of paper can't get brighter without increasing the light in the room, which is not something that people can control. So if you want your colors to be vibrant and bright, that's great, but it's not going to be as bright as on your screen because light is directly coming from your screen to your eyes. So just keep that in mind when you choose colors. That it might not translate well to print. Switching back, I'll only go to Photoshop one more time.
Let me make sure the audio is still working here.
Good.
I think it is.
Okay, so with the audio still working, we're going to get into some stuff here. I'm going to have to go a little fast because I only got 35 minutes left. So make sure you stop me if you have any questions. But I recognize that some of this is going to be a lot of gobbledygook. Follow it as much as you can, and then ask for clarification if you need that. But I am going to go fast without getting that feedback. So we're going to start with bits. zeros and ones. This is called binary. And it's also called base 2. And we should probably know what base means. So our current system is called base 10. Let's write the digits that we use in base 10. You can zoom in on this, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and there's no other digits in base 10. There's 10 digits. Now you'll notice that there's not a digit to make 10. It takes 2 digits to depict this many things. So if we want to depict this many things in our system of writing numbers, we have to use 2 digits, a 1 and a 0, to indicate this many things. So let's look at another base. Gonna look at base 8. And how many digits do we have in base 8? Given that we've got 10 digits in base 10, how many digits do we have in base 8? 0, 1, 2, 3, 4, 5, 6, 7. You'll notice there's not an 8 in base 8. Just like there's not a digit called 10 in base 10, base 8 has 8 possible digits. And if we wanted to write, if we wanted to depict this many, which you all know as 8, but in base 8, to depict this, it's 1, 0. That is how we write this many in base 8, 1, 0. So if we go back to binary, base 2, how many digits in base 2? If we follow the pattern, it's 2. Got 0 and 1. You'll notice there's no 2 in base 2. If we want to write this many, then it's a 1 and a 0. So we've got 10 in base 10, 1, 0 in base 2, 1, 0 in base 8. These 3 numbers look the same, but they mean completely different amounts. This one meaning this many, this one meaning this many, and this one meaning this many. So what would be the, how would we write the next number in the sequence? So let's take base 10. We know that this depicts this many, 10 things. So the next one we write is 1, 1, and that depicts 11 things. In base 2, if we were to write 1, 1, that would depict 3 things. And if we did it over here, that's how we would write 9 things. So without getting too confusing, let's look at why that is. We'll start with base 10. Let's use 246. So 246, this is the ones place, the tens place, the hundreds place. Does that sound familiar? Remember talking about ones place, tens place? But if we really think about what that is, it is the base 10 to the 0 power, to the first power, to the second power. Anything to the 0 power is 1, by definition. Anything to the first power is itself. Anything to the second power is the base times itself. So in this case, We've got 6 times 10 to the 0. 10 to the 0 is 1, because anything to the 0 power is 1. We've got 6. We've got 4 times 10 to the first power. Anything to the first power is itself. 4 times 10 is 40. And we've got 10 to the second power. That's 10 times 10, which is 100. 2 times 100 is 200. And if we add these all up, we got the same thing. All right, you're not as impressed as I would like you to be, because we ended up back where we started. But what this is doing is showing you how this works with base 10. Now let's apply it over here to base 2. Let's take 1, 0, 1. This is 2 to the 0 power. Anything to the 0 power is 1. 2 to the first power. Anything to the first power is itself. To the second power, which would be 2 times 2. So we've got 1 times 1, which is 1. 0 times 2, which is 0. And 1 times 4, which is 4. We add those together and we get 5. So 101 in base 2 is this many things. 5. And that's how we write it. 101. But to indicate that this is not 101, we've got a couple ways to indicate that it's a different base. Generally, we use a subscript of the base. And that means that you move it down a little bit to the right. It's kind of the opposite of when you say to the power of something, which is a superscript, which is up a little bit to the right. This is down a little bit to the right. And that indicates that it's base 2. We could also say base 2. We could write that out. And then let's do base 8. Let's do 2. What did I do over here? 246. Let's do 246. 8 to the 0 power, 8 to the first power, 8 to the second power. Anything to the 0 power is 1. 6 times 1 is 6. Anything to the first power is itself. 4 times 8, 32. And anything to the second power is itself times itself. So 64 times 2, 128. We add those together. 16, 4, 6, 166, base 10. So when we write 246 in base 8, that is the equivalent of 166 in base 10. So this is how you convert them back and forth between base 10. But it begs the question, if we can have all these bases, why do we have base 10? What's special about base 10? Why do we have it? Why don't we use this? Why don't we use binary? Why don't we use octal? Why don't we use some other base other than 10? Does anybody have any ideas? The clock is ticking. Any ideas at all? Why we use base 10?
We have to wait a little bit for the chat to pick it up.
It's all right.
Common convention to do so.
Common convention, but why is it a common convention? Because it is a convention. It is a convention, for sure. It's one that we all agree on. There is no universal rule that points us towards using base 10 to write our numbers. Our number system, everything is based on base 10 in our number system. Why? Why is it 10? Don't overthink it.
Someone in the chat room says, we are a base 10 style society, and we have 10 fingers.
Yeah. We have 10 fingers. This is why we have base 10. Because we have 10 fingers. If we had 12 fingers, we'd be using base 12. If you had 8 fingers, like the Simpsons use octal, base 8. This is definitely because this is how we learn how to count things it makes sense that, that when you see kids saying how old they are, whatever, they're using their fingers because they can relate to this being an amount. Because numbers represent whole numbers represent something that you can count. And that's what we're dealing with here. So let's look at one more. Gonna look at base 16. Base 16. How many digits in base 16? If we follow the pattern, there's 16 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. Whew, we're out of digits. But I need 16. So we got to come up with some way that we have a digit that represents this many that we can write with this in a single symbol.
Did you switch markers? That one's starting to fade out.
Yeah, I thought that was a good one. Can you see? Does it need to? Oh yeah, look at that. I just mixed them up. This is the good one.
Is this showing up now on the screen? Can you switch over still?
So we're looking for the other, the remaining 6 digits for base 16. We need some way to symbolize the number 10, and we can't use a 1, 0, so we've got to come up with something. You guys have seen this. I'll give you a hint. It's on the. This is where we're heading. So what's next? If we're counting. 5, 6, 7, 8, 9. The next digit. Base 16. No guesses?
Any guesses in the classroom? What would you put after 9?
10.
Okay. How would we write 10?
You had to make up a symbol.
A.
Yeah, there we go. So the digits in base 16, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. F is equivalent to this many, which we call 15. Here we call it F. So how do we do a 16? Just like the other ones, it's a 1 and a 0. This is how we write 16 in base 16. 1 and 0. And we have to indicate that it's base 16 so we don't confuse people. Otherwise they'll think it's 10. When the 1 and the 0 is actually 16. So how does that work? 16 to the 0 power, 16 to the first power, 16 to the second power. So the 1's place, the 16's place, and the 256 place. So give me a number. Just give me some digits. I just need 3 digits. Let's make the first one smaller. So we're going to do 2. We'll throw in a C, and let's do an A. 2CA in base 10. What is that? I'm sorry, base 16. What is that equivalent to in base 10? So anything to the 0 power is 1. 1 times A is A. We're going to translate that. We know that A is actually 10. 16 times C, we've got 16 is 12, so 12 times 16. I'm not going to do that in my head. Somebody.
192?
Thanks. 192. And 16 times 16, 256 times 2 is 512.
There are people in the chat room helping out with this and saying it looks like a lot like RAM, like memory amounts in a computer.
Yeah, because that's where we're going. That's where we're headed with this. So if we were going to write the number 714 base 10, if we're going to write it in base 16, it would be 2CA. And there's a couple ways to designate base 16. 2CA, you could use pound sign. You cannot use a hashtag. It's a pound sign. And you can also say this is a 0 and a lowercase x, and then 2CA, and this also represents base 16. So these two symbols are used to designate base 16, and then the third way to designate base 16 is a subscript, where you just put the 16 after the number. So why are we worried about this? We're going to go back to binary. We're going to use 8 digits here. We've got a range from 0000 to 1111, and let's figure out how many different combinations that is. If we go 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 1 times 1 is 1, 1 times 2 is 2, 1 times 4 is 4, and 1 times 8 is 8. 12, 13, 14, that's 15. So I'm going to put the 15 in parentheses, and up here I'm going to put a 0 in parentheses. Because this range, 0000 to 1111, is between 0 and 15. So there's 16 possible combinations with these 4 binary digits. Binary digits are shortened to be called bits. Binary, dig, it. Binary, dig, it. Bits. So when you've got 16 possible combinations here and 16 possible combinations here, that's a total, 16 times 16, of 256 possible combinations if you were to use 8 bits. And 8 bits together is called a byte, which is the basis of everything we mentioned when we talk about computers. Kilobytes, megabytes, gigabytes, terabytes, no, after tera.
Exabytes?
Hexabytes. So it just keeps on going, but everything is, basically you're counting binary digits, zeros and ones. This is what the computer likes. Petabyte. Thank you.
Thank you, chat room.
Yes. The zeros and ones the computer likes. It's an on-off switch. It's true or false, 0 or 1. That is what your computer is, that's how your computer is thinking. But if we were to have to use these numbers, these binary digits, and string them together, it would be nonsense to us. Our brains could not process them. So what we do is we translate those to base 10, and that seems to work out pretty good, and you're probably used to seeing 256 of things a lot. You're used to seeing a range of 0 to 255 in IP addresses and all kinds of situations, and they're really talking about a byte. So because it's 256, and because when we go into base 16, if we were to do F, and another F. Now this, and we're going from 0 to FF, just like we did here, 0, 0, 0, 0, 0, 0, 0, to 1, 1, 1, 1, 1, 1, 1, 1, 1. Then it would be the same range, 256 possible combinations, because this is 16 digits, 16 possible combinations. This is 16. Multiply them together, you get 256. So this kind of matches up. So what we've done is we've decided to do a compromise, because nobody's going to expect you to be able to write a string of binary digits. But what we've done is shorten these two pairs of 4 down to 2 pairs of single digits using base 16. And that's basically why we use it. Oh, I'm doing good. So that brings us to this. We have a schema for writing out color values using base 16 that is pretty universal at this point. And we use the pound sign to designate that it's base 16. And we put them in 3 pairs of 2. And keeping in mind that each of those pairs is going to have a value between 0 and 256. So this has a value of 0 to 256, 0 to 256, 0 to 256. So if we take 256 times 256 times 256, somebody's going to have to calculate this for me. What?
16 million
16 million.
777,216.
216. Boom and boom. And this is what's referred to, and has been for many years, as millions of colors. The combination of 3 256 range values gives you a possible combination of over 16 million colors. And the way that we've decided to do that is to take this RGB and attach it to these 3 pairs. R, G, B. So that is now, if we have 256 combinations for red, 256 possible, not combinations, but values. Values for green, 256 possible values for blue. How many bits are we talking about? Keep in mind that a byte, 8 bits, is the equivalent of 2 color values, or 2 X values. So we've got 8 bits here, 8 bits here, 8 bits here. Total of 24 bits. So sometimes we call it millions of colors. Sometimes we refer to it as 24-bit color. And that's why. So let's look at, given the time, let's translate this to actual colors so we can get some numbers. Out. So let's write red, pure red, maximum red. What would that look like in terms of writing that in base 16? Given that it's RGB, so the first pair is red, second pair is green, third pair is blue. We want the maximum value for red. And then you need to include the other 2 pairs. So this is red, green, RGB, blue, white. Any guess on white? These are additive colors. This is coming from your screen.
It's like painting with light, right?
Yeah, painting with light. After you get that, we need to get black.
So I'm still waiting on the chat room here, but I like to think of white as painting with all the colors of light. So can you guess in the classroom how you write white?
Will this be all F's then?
Yep.
All F's,
And for all black. So you should be able to memorize these. Everything else you're gonna have to play with to get accustomed to the mixture of these things. We're gonna play with it a little bit, 8 minutes, on Photoshop. Last time I'm going to Photoshop.
All right, and this is where we're probably gonna lose audio for a minute. I promise to fix it as soon as I switch.
Oh.
All right. Is audio working still?
Check. Check test. I'm seeing a thumbs up, so we looked at, just gonna try to get the big mouse here. We looked at yellow. We looked at this RGB value here. Right below it, you see a pound sign. And you've got these values here. We can also type those values here. So let's start with red, FF0000, there's our red. If we wanted to do green, 00FF, FF 00FF00. There's green, maximum green, and blue. 0000FF. There's blue. Notice that we can't print that blue. And white, which was maximized. FFFFFF. And black. 3 pairs of zeros. So now we start looking into mixing those. So if we have maximum red, maximum green, and no blue, so this is red and green, that's what makes yellow. If we have red and blue, FF00FF, that makes purple, but it's really magenta. And if we go 00FFFF, and then here's cyan. And so when your teacher was talking about blue, and you were mixing the blue and the yellow and getting green, the theory behind it was you were mixing the cyan and the yellow, and you were getting green. Is what was really happening. And that's what you're accustomed. So you just kind of got to flip to this new color space, RGB color space. Photoshop does have a way for you to experience the CYMK color space on your screen. It's a simulation of what things will look like once they're printed out, and it works pretty good. So if you're doing design work that is ultimately going to be printed and it's not going to appear on the screen, then it's a good idea to switch Photoshop over to the CYMK color space. But most people that know that they're doing a digital medium like a screen, like a website, digital photos, film, anything that is primarily going to be in the RGB color space, then you should be working in the RGB color space because it's going to give you a much greater range of brightness and colors. And then if that ends up needing to be printed, then there's some techniques to then adjust that to make it look better on print, but it's never going to look exactly the same on print as it does when you're on your screen. So you have to keep that in mind when you're starting a project. What am I going to use this graphic image for? What am I going to use this photo for? And then that may determine which color space you edit that in Photoshop. So I got 4 minutes. Any questions? This is a record for time.
This is a record for time. Can you bring up the slides while we have 3 minutes left?
Absolutely. Oh, here we go.
So as you've been playing around with colors in CSS, I hope you've seen the hexadecimal versions of colors. That's not the only way that you can describe colors in CSS now. And if you would prefer to work with the RGB format, where you can see the 0 to 255 range, that's possible too. The good news is Photoshop and Atom and the Web Inspector will let you see color in all 3 formats.
Since you mentioned it, I should point out that you refer to it as hexadecimal. You can call base 16 hexadecimal or hex, and people will understand when you're saying hex that you mean base 16.
There's one thing on this slide that I don't think we've talked about, and I think we should point it out. There's the RGBA and HSLA way to format color, and it adds one more dimension. Do you want to talk about how that relates back to the bits?
Yeah, when we talked originally about 24-bit, there's also 32-bit color, and that involves a fourth channel where you've got another pair of FFs, and that's another 8 bits, range from 0 to 256, and this is the alpha channel. We've got RGB and alpha. And alpha is transparency. So if you've got you've got a range of 256 values of transparency, which depending on the format that you put those in, that will be respected by web browsers. An example would be the PNG format or the GIF format. Those two will respect the alpha channel, and in addition to that, then you've got this notation if we go back to the PowerPoint.
Yeah, the one difference from what we wrote on the whiteboard here is the alpha channel in CSS isn't really a number of 0 to 255. It's actually a percentage.
Oh, that's right.
And they like to think of it, I like to think of it as like transparency, only it's kind of like the inverse of it. It's like the opacity.
Yeah.
So if you specify a color with RGB, it's assumed that it's 100% opaque. If you wanted to make it 50% so that you can start to see the background bleed through, you add the RGBA format, and then in that last 4th digit, you specify the color digits RGB. When you get to the A portion in that CSS property, you actually specify a percentage. Only you have to write it as a number, so that would be like 0.5 for 50% transparency or 50% opacity. It's pretty nice to let colors bleed through like that because the colors start to mix then, which is always fun when you start painting with light. The HSL and HSLA, those are, our textbook does a great job of covering those. Those are a different way to think about the color wheel. Do you want to talk about the color wheel at all? Or, let's see, how are we doing on time?
We get 23 seconds.
23 seconds, all right. There's a website called I think it's color.com, right? It's Adobe Color. Well, I'll put the link inside of Moodle.
Okay.
It allows you to pick out a color scheme where you can use a color wheel just like in Photoshop. If you don't have Photoshop, the color website from Adobe is free. You can start to build up complementary colors, pair colors on different ends of that color wheel to make an effective color scheme.
Ooh.
I wanted to mention a few other things. I know that the timer is going off. If we're using Atom, which I know many of us are, you can actually install a plugin called Color Picker. And then any place where you write the hex for a color, you can right-click or hit the keyboard shortcut Command or Control-Shift-C, and that will pull up a little color picker, a lot like the one in Photoshop, which will allow you to pick the color that you want. And then one other thing, we worked on the web inspector last week. It doesn't matter if you're using Chrome or Firefox or Safari, all three of them now feature an impressive color picker that lets you switch between hex, the RGBA, and then the RGBA formats for listing colors. So all of these are really powerful tools that I wanted you to be aware of if you don't have Photoshop.
Thanks, everybody. Record time, and
Yeah.
no questions. We good?
I want to thank everyone for joining the live stream. I know that the audio cut out and the video cut out a little bit. Can you hear me? Okay. So thank you everyone for joining the live stream. I appreciate you working through our technical struggles here. We will post the recording as soon as we can. And if you have questions about color, feel free to post them in Slack, and I will relay them to Anthony. Yeah, the sound will pick up in a second. So thank you again, and I'll see you next week.